My name is Avinash Gupta. I am from Oklahoma State University. I am doing my PhD in computer science. My area of research are virtual reality-based applications, information modeling, and information exchange. So, good afternoon to you all. I hope you had a good coffee break so that will wake you up for this presentation. So today, I'm going to talk about design of IoT-based smart surgical simulation environments for orthopedic training. So you can see Dr. Cecil, he is the project lead, and Avinash that's me. We are from Center of Cyber Physical Systems at Oklahoma State University. We also have Dr. Cruz, who is MD, who is an orthopedic surgeon, and he has been with us through the entire process of design, development, and assessment of the surgical simulator. We also have Dr. Ramanathan, who is a professor at University of Wisconsin-Madison. He is the main networking guy. He's for the data exchange and for the GNS that I'll go ahead and discuss. So providing a brief outline about our presentation, I'll start with introduction, then I'll give the problem statement and what are the objectives of our project and this paper, a sort of overview of the list plating surgical process, which is the surgical process in focus, and then we'll talk about the two simulation environments which make up the IoT-based framework, and then we'll talk about the assessment, and then I'll finally conclude the presentation. Okay, so if you go back 15 years, I mean the VR was still in its infancy stage. There were not a lot of VR simulators developed, but now if you look at it right now, there's a rapid increase in the use of VR simulators, especially in the field like automobile manufacturing, space system design, shipbuilding, among others. The field of medicine has started adopting VR-based technologies, and there are several simulators available for heart surgery, laparoscopy, arthroscopy, among others. As I just mentioned that there are a lot of surgical simulators available for heart, arthroscopy, and other surgery. There is a lack of VR simulators in the fracture treatment area. If you look at the simulators for orthopedic surgery, most of the simulators were designed for arthroscopic surgery, but there is not a lot for fracture treatment. So that was one driving factor behind development of this simulator framework. Also, there are different drawbacks in current training methods. For example, currently, how do residents learn? They learn by seeing the surgeon's practice. They also learn by practicing on cadavers and animals. All of them have several drawbacks, and we focus on designing something that will try to supplement these training methods. Also, there is a need for collaborative training so that the people can learn from remote locations and learn collaboratively through surgeons and other practitioners. Let's talk about our prior work. So previously we have created non-network based haptic simulator and also immersive power wall environments where we have to use 3D glasses, and then a lot of people can at the same time look at the simulation and learn from it. And this paper focused on development of cyber physical framework, and the framework consists of two simulators. One is the haptic based simulator and the other one is mixed reality based simulator. I'll go in details in the coming slides. So this is our cyber physical framework. On the cyber side, you have got the training modules, you have got the cyber physical manager, and on the physical side, we've got the haptic device. The human is also a physical part of it. And for the mixed reality training environment, we've got training headset used such as Vive, and also we'll have 3D printed parts that can be used to train, as seen in the diagram there. So the focus of the simulators is LIST plating surgical procedure. LIST stands for less invasive stabilizing surgery. It is a fracture treatment surgery for femur bone. So let's dive into details of how a typical LIST plating surgical process is performed. So the surgeon first does a preoperative planning, and then he chooses implants based on the intensity and location of fracture, and then fracture reduction is done. So what is fracture reduction? Fracture reduction is bringing back the bones into their original position after they are fractured. And then after that, LIST assembly is done, where the parts are assembled outside of the patient's bone. This is the part that's assembled outside the patient's leg, and then it's inserted inside the patient's leg. And then the screw are tightened to attach the plate inside the bone. And at last, insertion guide is removed and the wound is closed. You can see a presentation of a reflection of the list plating guide and the other tools in the picture here. Before diving into the simulators, let's take a look at the approach that we use during the design of our simulators. We use an approach called information-centric systems engineering. This is not the scope of the paper, but I'll go through it quite in brief. So we develop models to plan, design, build, and validate our systems. And also we build models which are process models to understand the list plating surgical process. And each model has a top level, and they are decomposed so that we will get the task in the lower level as well. And EML is used to design this models, which is a evolving language. So let's talk about the first environment, which is the haptic-based training environment. Haptic refers to sense of touch. So this haptic device, geometric touch haptic device, provides users a chance to touch, hold, and interact with the implants and surgical tools. So if this surgeon or resident picks up something, you will feel the weight of it. And also, if suppose she is drilling onto the bone, it will provide feedback so that you will feel that you are drilling into the real bone. So this is one use of the haptic interface. As mentioned earlier, haptic-based environment is also collaborative, so that users from different remote locations can use it. Here is an overview of the IoT-based interactions that takes place in the framework. We have got users in several locations: Oklahoma, El Paso, where Dr. Cruz is from, and Madison, where our other collaborators from. And they interact with each other through the Genie network. I'll be discussing about Genie in the coming slides. Okay, as I mentioned earlier, haptic-based simulator is network-based simulator. So there are two modes of training. One, the users can interact with the cloud-based simulator without interacting with other people. And second, collaborative, where more than one people can collaboratively learn the processes through interaction with each other, again through the cloud. So for this design, we have used Genie, which is a next generation applications, and it has got features like it has got multi-gigabit bandwidth, it has low latency, and it also provides software-defined networking capabilities. And while testing, we also tested the latency, and during the test between 3 haptic users, the latency was around 40 to 42 milliseconds, which is acceptable for such scenarios. Now moving to the fully immersive mixed reality training environment. This is a unique approach where we use green screen, Vive headset, and SD cameras, so that the user can interact with real world and virtual world at the same time. So the room is covered with green screen, as seen in this table, as seen in this picture, and you can see the user wearing the Vive headset, and you can also see the camera here. So what does the user see? In the green screen, everything is erased, and you will see the virtual environment there, but whatever is in front of the green screen, you will see it through the cameras. So the end result would be a virtual environment where the avatar or where the surgery process is going on, and this user is trying to follow those steps and try to replicate that in the real world using the real tools and environment. So let's go and see how the mixed reality environment works. So there are 2 cameras attached in front of the Vives, and they project 2 images on a plane, on 2 planes, and these planes intersect with each other. And when viewed from the Vive headset, the 2 cameras provide a 3D interface so that they could visualize, rather than 2D data, they will visualize the real objects as 3D images. Now we'll focus on the scope of training environments as mentioned earlier, there are several steps involved in the list plating surgery. So based on those steps, we created training modules. For example, the first one is list assembly training module, training environment where they assemble list plate. Then we move on to list insertion training environment where they insert it inside the patient's leg. List position training environment is an important one where they try to position the list plate in the correct position and orientation. Then we move on to fracture reduction training environment, screw insertion, and finally we remove the guide from the user's leg. Here is a view of the position training environment. As I mentioned earlier, positioning the plate inside the human's leg is very important, and it's important that we position it correctly. So we have used these red light, green light concept. So whenever the bone is in the wrong place, it will show red lights, and when the user is able to position it in the right place, the green light will pop out on those windows. Here's another view of the screw insertion training environment where the user is trying to insert the screw inside the patient leg to tighten the list plate with the bone. So this project, we have got an interdisciplinary team consisting of computer scientists, engineers, and surgeons. So the surgeons have been the part of the team since the beginning of the project. They discussed details, they answered questions, and also they played an important role in creating the information-centric models. And then we interacted with surgeons in conducting the learning assessments, and they validated the system by modifying and changing the capabilities of the system. Now moving on to the assessment part. After the system was validated by the surgeons, we wanted to assess it on the medical students and residents. So this study was conducted at Texas Tech University Health Sciences Center, and this study was conducted over 4 years' time, and around 60 medical residents and students were involved in this study. And this study involved two thrusts. One would be standalone haptic simulator, where the students interacted with the cloud-based environment without interacting with anybody else, and the second would be the collaborative one, when the surgeon was present in a different location and the users were present in different locations, and they interacted through the cloud. And during this stage, first they took the pre-test and they asked several answers related to the list plating surgery. Then they interacted with the simulator, and then they later conducted the post-test. So that's how this assessment took place. Here are the results from the standalone haptic simulator. Currently 45 participants have participated in the surgery, but participated in the test. But at the time when we published this paper, we had 32 participants. Out of the 32 participants, 27 showed improvements. And the surgeon rated the improvement in two categories, significant and moderate. When a participant rating was over 40, it was rated as significant improvement, and when the improvement was less than 40 points, it was rated as moderate improvement. And also 80% of the participants who interacted with the simulator told that the haptic interface provided them a better way to interact with the simulator. This is the results from the collaborative haptic test, where surgeons helped them with interactions. So 8 participants were involved in this study, and all of them showed improvement. 2 showed significant and 6 showed moderate improvement.
There's a typo there, the student improvement. Right?
Participants were satisfied with the performance with minimum latency. So let's go into the discussions. The conduct study shows the potential of such simulators can be used as a proper training tool, and the collaborative aspect of framework received positive feedback from the surgeons as well as the students. And the mixed reality environment is important because it allows users to interact with real and virtual world at the same time. So future work, we are planning to conduct transfer validity. Transfer validity refers to testing what you learned in one system and transferring it into another system. This we'll try to do by creating 3D printed mock-ups and trying to see what a student learned in the virtual simulators if they could do it in the real simulator as well. And we're also expanding the scope of training to other surgical processes such as condylar plating, which is again a different process to treat fractured bones. So finally, I'm going to conclude that IoT-based framework was discussed in this paper. We discussed 2 simulators for the framework, which was the one that used haptic device and the other one was mixed reality. The architecture was discussed, the risk surgery environment was discussed, and we also discussed about the results. Thank you.